So in this lesson, I'm going to cover Bitcoin transactions, basically cover how they work. So yeah, by the end of this presentation, hopefully you'll understand how transactions work, what they look like, and how to construct your own. So I've broken up this presentation like last time into 3 different parts. I'm going to start out with the basics of Bitcoin transactions. So I'm going to explain basically what they look like, what the data is representing, like so, and I'll cover everything you need to know about the structure of transactions and how they work. After that, I'll move on to the data. So instead of just giving you a visual representation of what the transactions are actually doing, I'll show you what the data looks like. So if you were to look inside an actual transaction, I'll show you how the data describes that and how it works. And after I've covered how they work and what the data looks like, I'll start doing some examples. So I'll construct a transaction from scratch just to show you how you can create your own Bitcoin transactions like that. So I'll start now the first part with the basics of how Bitcoin transactions work. So carrying on from last time, in the last video I covered how mining works. So if you remember, each of these computers represents a Bitcoin node on the network, and this is the entire network, and they are sharing this file here called the blockchain. So what happens is, when you want to make a transaction and send someone some money, what you do is you just create a single line of data. And so this little green line here represents a Bitcoin transaction, which is just a bunch of data, and you'll insert that into any node on the network, and then they will store it in their memory pool, and then they'll pass it on to the nodes they're connected to, and so on until everyone's got a copy of that transaction in their memory pool. And then all of these nodes then will compete to try and mine the transactions from their memory pool onto this file called the blockchain. So let's say this one does it, and after they've done that, they will pass on that block that they have mined to the nodes they're connected to. They will add it to their blockchain, and so on until everyone's got a copy of the latest block to be added onto their file. And when that's done, then this person can look at this blockchain and see that the transaction's in there, and because that transaction is now part of the blockchain, the ownership of this Bitcoin has changed from this person to this person. So today I'm going to cover how does this work, how can you create a single line of data like this, and how does that represent the change of ownership of Bitcoins. So I'll cover that now. So the basics of Bitcoin transactions. Let's say this green line here represents the data, and it's going to send or change the ownership of this Bitcoin from me to you. So if I blow that up, this green line here still represents the transaction data. I'm not going to show you the data yet. This is just going to be a simple representation of the actual data. First of all, this is the blockchain. Let's say this represents the blockchain. Carrying on from the last presentation, we know that it's just a bunch of blocks, individual blocks containing transactions. So the blockchain is just one big file of transaction data. But because we're looking at transactions today, a good way to visualize what that transaction data represents in the blockchain is a bunch of different batches of Bitcoins. So each of these little orange boxes here represents a individual batch of Bitcoins, and each of those batch of Bitcoins has a lock on them. And so that's how people can own Bitcoins, because a lock is placed on them so that only the people who can unlock them will be able to spend them and send them to someone else. So basically the blockchain, if you sort of visualize what it's representing, is a bunch of lock boxes, like in a bank, like this, all different sizes of Bitcoins. So if I move that to the side now, we're going to construct a transaction and move Bitcoins from me to you. So if I was to construct a transaction in the first part of the data, so this is the data, what we do is we select a batch of bitcoins from the blockchain. Each of these batches of bitcoins have their own unique reference number, so you can select them. So in this first part, you'll put some reference code in here to select the batch of bitcoins you want to send. Then in the second part, or the second half of this first part of the transaction, you need to be able to unlock this batch of bitcoins. So what you'll do is you'll put some unlocking code or use your private key to be able to prove that you can unlock this particular lock, like so. So that's the first half done. Just select a batch of bitcoins and unlock them. And then the second half of the transaction, you just create a new batch of bitcoins, and you will put, in the second half, you'll put a new lock on it. So this was the original batch of bitcoins that was locked to us, and in this transaction we've taken that batch, opened it up, created a new batch from it, and put a new lock on it. And this lock is locked to this person's, say, address, which is like an account number. And so that is a very simple transaction. Just select some bitcoins, unlock them, create a new batch, and put a new lock on them, and they are locked to this person here. So when you think of making a transaction, it's best not to think of it really as having some bitcoins and then transferring them across the internet to someone else. That's not quite how it works. What really happens is you have a set of keys, like an address and a private key, and someone else has their own address and private key. And when you want to send them some bitcoins, you just go into the blockchain, select batches of bitcoins that you can unlock with your private key, and then you will create a new batch of bitcoins locked to the other person's address so that they can then send them on using their private key. So again, for example, if they want to send this batch of bitcoins onto someone else, they'll just use their private key to unlock this particular lock that we created for them, and they will send them on. So as you can see, bitcoins sort of form this chain of transactions as they move from one person to another. Up until now, I've been calling these batches of bitcoins, but their technical term is outputs. So from here on out, I'm going to use the word output to describe what to call these batches of bitcoins. So obviously, all of these batches in here, they are all called outputs. So everything here, all these orange boxes, are outputs. But to be clear, when we refer to an output, when we're spending an output in a transaction, we refer to it as an input. So every transaction takes an input and creates a new output. What we do then, we'll send that transaction into the Bitcoin network, and hopefully it'll get mined onto the blockchain in a block. So imagine this is a new block of transactions. This is our transaction that got mined onto the blockchain. And if we were to sort of visualize what's just happened, this output we spent, so I've graded out, it can't be spent again. And in this new block, thanks to my transaction, I've created this new output that belongs to this person here. So that's how transactions work on a very basic level. In the last example, I sent an entire batch, a whole batch of bitcoins, and I spent a whole batch, and created 10 bitcoins as the amount I'm sending. But you don't actually have to use. But what if you want to send less than 10 bitcoins? So you have this batch 10. What if you want to send less? Well, you can do that. You create an output that sends, 8. Say I want to send 8 to this person, but there's obviously 2 left over. So what you do is you will create another batch of bitcoins as the change. So we've taken this input here, created an 8 output from it that gets sent to this person, and then we'll take care of our own change, and we'll lock that to an address that we own. So that's how you take care of change. You basically take care of your own change when you make a transaction. Up until now, I've just been using whole round numbers of bitcoins, but you can actually break bitcoins down into very small numbers. So for example, I could send them a very small amount and send myself the rest in change. This is perfectly fine. There's no, real restrictions on, there's no restrictions on breaking down the Bitcoins. This is the smallest unit of the currency. It's called 1 Satoshi, and that is 8 decimal places. So this is how far you can break down a Bitcoin. You can't break it down any further than that. Similarly, say you have this batch of 10 Bitcoins here, but you want to send 30 Bitcoins to someone. What you can do, instead of just creating 2 separate transactions, if you own various outputs that belong to you, you can collect them together. As long as you can unlock them, you can collect them together as inputs to create this much bigger output. So there's no limit to how many inputs you can select from the blockchain in your transaction. As long as you can unlock them, that's fine. And again, this is 10 and 25. I sent 30 to this person, so there's obviously 5 left over in this transaction. So you want to take care of that as your own change. So like I said, with every transaction, you have to take care of your own change. And like before, when this transaction gets mined onto the blockchain, same again, we'll have this 30 output here locked to this person, and then we'll have this output for ourselves that's locked to us. And both of these that we selected from the blockchain have been grayed out because they've been spent in this transaction. And that's how the blockchain that's how transactions work in the blockchain. So yeah,
Hey,
go on.
great. So quick question. So in the last slide, you're saying that one transaction can have inputs from multiple transactions.
Yes, exactly.
Previous transactions.
Yes.
Okay.
You can have as many inputs as you want and create as many outputs as you like. Yep.
Right. And both these inputs need to be obviously owned by you.
Yes.
Right?
Yes. Well, I mean, as long as you can unlock them. Yes. I mean, if they're owned by you, if you have the keys to unlock these, that's fine.
Yeah. The assumption is that if you have the keys, you own them. So okay. So you can take multiple inputs from transactions that people have sent you. Let's say that 3 people sent me $5 each, and I want to send someone $14.
Yes.
I can use the inputs from those 3. I can create one output for $14 and $1 back to myself.
Yes, exactly.
Right?
Yeah, that's
cool. Yeah. Awesome.
Right. So that I've just been showing you one individual transaction here. This just is one individual transaction. So if you were to go back in time and visualize all the transactions as they're being added to the blockchain. So this is the first transaction here. Then we have another transaction that spends this output like so. And then we have another block of transactions. We have another transaction that gets spent, and so on, like this. So with every new transaction that gets made, it builds this sort of graph structure. So like you asked just then, you can take different outputs from different transactions and collect them together to create one single transaction. But as you can see, with every transaction, they're all connected together, and they create this chain of outputs. So inputs, outputs, and so on. So when you make a Bitcoin transaction for yourself, you just select any available outputs that you can spend from this graph in the blockchain, and then you create new outputs from them. So a single transaction will have this effect on the Bitcoin transaction graph, like so. So this is probably the best way to visualize the blockchain. I mean, you could think of it as having just individual outputs, but they are actually connected through series of transactions. So the blockchain looks like this, but obviously on a much, much bigger scale. These orange outputs here, they haven't been spent yet, so they're called unspent transaction outputs, or they are referred to as UTXOs. So if you ever see the term UTXOs, it's basically referring to these unspent Bitcoins. And these are important because these tend to get held in memory by your Bitcoin client so that they can be accessed more quickly. Coinbase, so where do these original, obviously with these transactions so far, I've been referring to outputs that have already been made, but where do these first ever Bitcoins come from? Well, with every block that gets mined onto the blockchain, each block makes available a brand new batch of Bitcoins that a miner can send to themselves, and this is called the block reward. So when a miner mines a block, they will send the block reward or create an output from the block reward and lock it to an address that they own. And the way that they do this is in every single block of transactions, a miner will construct a block of transactions, but the very first transaction at the top of a block, that is a special transaction called the Coinbase Transaction, and that is reserved for a miner, and it is through this Coinbase transaction that a miner can collect the block reward. So basically, like I said, with every new block that gets added, a miner will essentially create new Bitcoins that did not exist before, like so. Does that make sense?
Yes. So is it correct to say that, the Bitcoin transaction tree, the first level of the Bitcoin transaction tree consists of only Coinbase transactions?
Yes, that would be the root. Yeah, that would be.
Yeah, the first level, you can
Yes.
say. Like every Bitcoin that's being spent today has its source to some Coinbase transaction.
Yes, that's right. So if you were to sort of turn this graph on its side, so this was at the bottom, all these transactions you're making, they have a route going down to these source.
To a Coinbase. True.
So, not all outputs are necessarily connected to each other, but they will always be connected to a source block reward.
Yes.
Finally, in this first sort of basic introduction, you probably might be interested in fees, transaction fees, how they work. So I'll cover that now. When you make a transaction, if you want to put a fee on it, well, let me just start again. Basically, when you make a transaction, if you want to put a fee on it, you basically do not use up the whole amount that you're spending. So this input is 10, and if you created outputs of 8 and 2, that would be using the whole amount up. But if you do not use it all up, and so you create a remainder, that remainder is the fee. So when you want to put a fee on a transaction, you don't create a separate output for it, you just leave a remainder of inputs that are not being used up. So let's say this transaction has a fee of 0.1 Bitcoins. We'll send that into the network, and eventually that'll come into the memory pools of all the nodes on the network. So the reason you put a fee on a transaction is because a miner, when they create a candidate block, they can only fill it with a certain number of amount of transactions or a certain size. So basically it used to be 1 megabytes worth of transactions. The metric has changed to weight now, but it's roughly about 1.7 megabytes worth of transactions at the moment. So if there's more than 1.7 megabytes in the memory pool of transactions, a miner will select the transactions with the highest fees. And the reason they do that is because, so let's say these little yellow discs represent the fees. These are the highest fee transactions. The reason they do that is because they can collect all of these fees or recycle all of the remainder of these transactions into the Coinbase transaction. So instead of just sending themselves the block reward, which is currently 12.5 Bitcoins to themselves in the Coinbase transaction, they will also include all the fees from the transactions they have included. So there we are. This block gets mined, and this Coinbase transaction recycles all the fees and creates a new batch of Bitcoins with the block reward in it also. Does that make sense so far?
Yes.
Okay, great. So that's all the basics covered. So that's all the structure of how transactions work, like a visual representation, taking inputs and creating outputs. What I'm going to do now, I'm going to cover the data. So if you're to look inside, well, basically, how can you construct your own transactions from the data itself? So this is going to be a bit more technical. So, if you're not a technical person, this should cover everything, all the interesting, under the hood mechanics of transactions. But this is more for, the programming and stuff. Right. So the data. This is the graph from before. And so whereas before I had that green line to represent the data, this black box here is like my editor where I'm going to go into create a transaction from scratch. So with every transaction, the first thing it starts with is a version number, and that just sort of describes the structure of the upcoming transaction, and that is currently 1. I'm pretty sure the majority of transactions use the version number 1, so just put the 1 in there and that's fine. But because this is a transaction data, it has a specific structure. So this version number, it's actually 4 bytes long. So this version field, is 4 bytes long. So we put the 1 in there, but we need to pad it out with zeros so that it's 4 bytes long. And 2 characters is equal to 1 byte. So this is 8 characters long, and that's 4 bytes. The reason we have these sort of field sizes is, well, basically everything in the transaction has its own field size. So that makes it easier to run through the transaction and decode it. Secondly, as well as being 4 bytes long, it has to be hexadecimal. So this is currently 1, so that's the same in hexadecimal. And lastly, probably most awkward from a human perspective, is that this data has to be in network byte order. So you have to reverse the order of the bytes. So that's the version done. That's the first part. Second of all, you have to put an input count. So you have to say how many inputs we're going to be using in this transaction. So if you had, 3, we'd put 3 in here. In this one, I'm just going to use 1 output. So I put the number 1 in there. And this is 1 byte long. However, this is a special field called a variable integer, and what that means, or reduced or shortened to variant. I think that's a technical term for it. I think it's sometimes called compact size, but variable integer and variant is what I've been used to. If the number of outputs you want to select is less than 252, or in other words, in hexadecimal FC, then you just leave it as 1 byte. So you just put it in here. But what if you want to send more than 200, we want to collect together more than 252 inputs, like so greater than this, but less than these 4 characters, then you just prepend the letter FD to the front, and then the next 2 bytes tell you how many inputs you're using, obviously in hexadecimal. Same again, if you want to do more than 2 bytes worth, a number that can't be held in 2 bytes, you prepend it with FE, and that means the next 4 bytes tell you the upcoming number of inputs. And if it's even bigger than that again, then I don't think this is actually possible, but it's used in other places. You just prepend it with FF, and the next 8 bytes tell you how many inputs you want to collect together. But for the vast majority of transactions, you're probably not going to be collecting together. I mean, if you're constructing them yourself, you're probably going to be using just 1 byte. So the majority of the time, this input field is 1 byte in size. So okay, that's probably all the most technical part done. Now we just move on to the inputs. This should be a bit simpler. So an input, we have to select an input from the blockchain. So the way we do that is, first of all, we need to get the transaction ID. So every transaction has its own unique ID number called a transaction ID, and you just shove that. That's the first part of this input code to select it, and that is 32 bytes long. It's also got to be hexadecimal ready, and also, again, it's got to be network byte order. So reverse this. So if you just select this and input it into a blockchain explorer, you won't be able to find it because it's been reversed. But if you just reverse it back, you'll be able to find it in a block explorer. So that gives you the transaction, but we want a specific output. So a transaction, like I showed you earlier, it can create multiple outputs. So what you do, you just use the vout, which is short for vector output. And so each of these outputs, starting from 0, has their own number. So this one has just one output, so I put 0 here. But again, that's 4 bytes long, hexadecimal, and network byte order. Next up, the next major part. So basically, we've gone,
So, just a quick question here. Let's say that we had multiple transactions, multiple outputs from multiple transactions. That's possible, right? So let's say we have 2 transactions and 2 outputs each from each of those transactions. So in the 0, 1 would become 0, 4, right? The inputs field. The one before that.
The input count.
Yes, input count would become 4.
It would be 2. How many inputs are we using?
Oh yeah, transactions. Yes. 2 inputs. Yes, that would be 2. And then would we list out all the transaction IDs, which are the 2, one after the other? Or
so what would happen is, say you wanted to select 2 different outputs.
Exactly.
This one here, this code here, this is for one single output. So if you had 2, you would just repeat this after this. Okay.
Got it.
Okay, so there we are. So we've selected this particular output from this transaction. So the transaction ID gives you this transaction, vout the particular output. So that's referenced this output successfully, but obviously it has a lock on it. And to be able to spend this and send it on to another person, you have to be able to unlock it. But in Bitcoin transactions, you actually have to construct the whole structure of the transaction before you unlock it. So I'm going to skip that for now and leave this blank. And this is called a script sig because you need to put your signature here, and all the code in here will be what's called a script because it has its own sort of scripting language. So it's called a script sig. But if you want to give it a more friendly name, you can call it unlocking code. Lastly, each input has a sequence number. This isn't used very often. I have never used it myself, but if you set this to a lower number than the maximum possible number, it means that you can replace the transaction later on. So say you put a very low fee on this, you can create a new transaction with a higher sequence number, and it will be able to replace the one that's already on the network. I've not done this myself, so basically I always set this to the maximum value of all Fs, because that's the maximum hexadecimal value. So I'll just move on from there. I usually just set this to all Fs. So that's one input done. Like you said earlier, if I wanted to select another input, I would just repeat this whole process just after this piece of code. Because you said 2 here, you can pass it easily. Next up, so that's the input done. We've selected this. Now I want to create some outputs from it. Same again. This is a variable integer. So if you wanted to, create lots of outputs, more than 252 or whatever, you just use the variable integer code. But because I'm only using 2 here, it fits inside 1 byte. And the reason for this, I didn't mention earlier, is just to sort of save space in the data, so that you can use less data where possible. So an output, this has its own structure as well. First of all, you put the value, how many bitcoins you want to send, but you don't put it the Bitcoin amount, you put the Satoshis amount. So say I want to send, I think this is about 0.02 bitcoins, you have to put it in Satoshis, so the smallest possible unit. So that's the first part of this output. That has to be in hexadecimal. It has to be 8 bytes long, this one, and also in reverse byte order. So when you look through code, this looks like gobbledygook, but if you just reverse the byte order and convert it to decimal, it will give you the amount. After that,
so this is Yeah, you mentioned this is 8 bytes long. So this tells me that there is probably some kind of limit to how much you can send in one transaction. Is that
Yeah, 8
accurate?
bytes hexadecimal. I think is a very, very large number. I have
2 raised to 8. Yeah, that's a
Yeah,
lot.
I
Yeah.
don't know.
Okay.
Yeah, but it's very. I think it should cover most cases.
Yeah, that's a lot. Yeah, yeah.
But it would be a good
Yeah,
problem to have.
yeah.
So after we've set the amount, the next part then, simple enough. You just have to put the lock on it. So again, this has the locks. They have their own sort of scripting language too, and they can be a varied size. So because they can vary in size, then they don't have a set size, like the transaction IDs or the version numbers. We have to use this variable integer again. So most signatures, typical signatures, are about 19. I think that's 25 in decimal, 25 bytes. So this just tells you the upcoming size of the lock. So you put the lock in there. Again, this is full of some code that creates a script that locks it to a particular address. So this is the address we've locked it to. We've used the public key in here. So I'm not going to cover this too deeply, but this code here corresponds to this particular address. And these grey things here, they're just the locking codes, the codes that lock it to this particular public key. So if you wanted to create your own lock, you can pretty much copy and paste this code here and just replace this public key with the public key of the person you want to send it to. And this public key can be derived from this address.
Right. So this locking code is obviously, it'll be different for different public keys, right? 76, A9, 14. Will that change?
The only thing that will change in a typical transaction is just this green part here. This 76, A9, 14, AC, they refer to specific codes in the script, and that basically just says this output has been locked to this public key, and if you want to send it on, you have to provide a signature.
Got it. This is basically the script that will run like. You put it on the stack, you check if it's equal. Are these opcodes? 76, A9,
that's
14.
Correct, yeah.
Got it.
I am glossing over. Yeah, these are the opcodes. These refer to as OP duplicate. Sure. But I'm glossing over these because I think the script code deserves its own video to be explained. Yeah.
Definitely, yeah.
So that's the locking code there. I don't expect you to understand this just yet. And like before, like you asked earlier, because I said 2 outputs, I just create another output here with the same structure as last time. So this part here, that's the amount I'm sending, and then this is the size of this upcoming locking code, and this is the actual locking code with a different address. So as you can see, this ends in 88AC, just like that one, and it starts with 76A9. So there we are. So all that's been changed here is the address that I'm locking it to. And then lastly, we have what's called the lock time. This is the final part of the transaction. And the lock time basically allows you to sort of post-date the transaction. So if you put a lock time in here of less than 500 million, then that's referring to a particular block height. So if you went back in time and we said we are currently at the block 14 and we put the lock time of 16 in here, then that means that this transaction can only be mined when the block height reaches 16 or greater. Similarly, if you were to put the lock time of greater than 500 million, so this 500 million here accounts for up to 500 million worth of blocks. If it's greater than that, then that means that you are specifying a particular Unix time, which is just the number of seconds since the 1st January 1970. But either way, this lock time locks the transaction up until a specific block or a specific point in time. But if you don't want to use it, which you probably don't, it's rarely used, you just set it to 0, so that means it can be mined immediately. And there we have a transaction. So just to go over it again, it has 4 main parts. You have a version number, usually 1, so just usually 1. Then you have the inputs. You just select an input. I haven't covered the unlocking code yet. We'll come back to that. And after the inputs, you have the outputs. Create the outputs from it, and then you have a lock time. And those are the 4 major parts of any transaction. Does that make sense so far?
Yes.
Okay. Going into the final part now of these slides, I'm going to cover this actual signing to create the signature to be able to unlock this output here, or this input. In this part, I'm definitely going to go through some things very fast, and I'm not going to be able to explain them in time because I think signing itself probably deserves its own video. But just in case you're rewatching this video and you're building your own transaction from scratch, I just want to cover everything that you need to do to be able to create the signature to sign this transaction. So bear with me. If everything doesn't make sense, don't worry. Maybe it will when you come back to it.
Sure.
So we have this transaction and we have this input that we need to unlock. So this has been locked to our address, and we have our private key that corresponds to this address. And we need to use the private key to basically prove that we are the owner of this address. So a bad way of doing this, or a very simple and bad way of doing this, would be just to shove your private key into a transaction. That would prove that that you have the private key. But the problem with that is when you send this into the network, you're basically giving your private key to everyone on the network because your private key has been exposed. Right. So if you had any other outputs that were locked to this address, they can use the private key to unlock them and spend them. Or they could just not relay this transaction. They could just take your private key and create a new transaction and send it to their own addresses. So that's bad. So we need like a more intelligent way of using our private key to unlock this lock to prove that we own this address without actually giving away the private key itself. And that's where signing comes in, using digital signatures. So like I said, this private key and address, they're actually connected. The address is actually created from your private key. I'm not going to cover how that works now, but they are connected through some mathematics using an elliptic curve. So what you can do, because these are connected with an elliptic curve, you can use some more mathematics to create a signature from your private key that'll prove that we'll be able to unlock this address. So I'll just run through it quickly. What you do to create a digital signature for this transaction is you take the private key along with the transaction that you want to sign, and you'll put it into this you use some elliptic curve mathematics, and that will give you a signature. And
right. So currently the right hand side input has just the information that is there on the screen, right? We it's still, the gap is still there, right?
Yes,
in the transaction.
Yes. So what will happen then? You've used this sort of unsigned transaction, and you put it into this function along with this your private key, and that will give you a signature. So this is a signature that will get put into the transaction. There we are. I've simplified this a little bit, so this is probably the part that you want to gloss over because it's hard to keep up. But I'm just in case you're watching this with a technical mind or actually doing it, what you need to do is first of all, when you want to sign a transaction, you have to kick out any existing signatures in there. So if you've already signed an input, take out the signatures. What you do then, you need to put a placeholder, some placeholder code into where the script sig is going to be, and that placeholder code is the locking code or the script pub key of the input that we're trying to unlock. This is just a placeholder so we know which input to sign. What you do then, you append what's called a sig hash type to the end of the transaction data. Not entirely sure what this is used for, but for typical signatures, you just put number 1. This is obviously a network byte order, and it's 4 bytes long. Then you hash all that together twice through hash 256, and that will give you this digest, which is the message, and that's what goes into this elliptic curve. Then that'll spit out a signature. You have to have this in a DER encoded format. I think most libraries will give you this option of encoding the signature in this way. And then finally, you need to append the same sig hash type to the actual signature itself. So this was a sig hash type before we put it into the mathematics, and then we append the same number. So this is 4 bytes, this is 1 byte. I think that was a mistake when Bitcoin was being developed to have these different sizes of bytes, but they're both the same number, 1 and 1. So that goes on the end there. So that's if you're doing it technically, but I just simplified this just to show you that the transaction data goes into this elliptic curve, and that gives you the signature. So when you've created this signature, because we use this elliptic curve, the address can basically look at this signature and say, okay, this signature could only have been created by the person who owns the public key that I made from. So that is good enough. This signature here is good enough to unlock this input. And by doing that, we can put this signature in here, and we're not giving away our private key. Another benefit of this signing process is because this signature is made from this transaction structure that we created. When we put this in here, if we were to send this transaction into the network and someone was trying to modify the structure of the transaction, like basically change where the bitcoins are being sent to try and steal your bitcoins, like so, they'll change the locking code, then this signature will no longer work, and this transaction will no longer be valid, because the signature will only work for the transaction that it's made from. So this signature here protects the structure of the transaction you've created, so that it'll only work for this particular transaction. So that's basically how you create a signature to unlock an input. This is called, like I said, a script sig. But in a script sig, you don't just put the signature in there. Because of the locking code in here that I showed you earlier, it also requires that you put the public key, which is like basically the ugly version of the address. You also have to put that into the script sig. So it's called a script sig. It's mostly signature stuff, but it also needs the public key for the unlocking code to work. Obviously, this public key can vary in size, so you need to put a variable integer here to describe how long it's going to be. Same thing for the signature, that can vary in size, so that has its own variable integer. And before the entire script sig, you put a variable integer here. So by doing this, because we have fixed field sizes and also variable field sizes, that means that you can decode this transaction and get the right amount of data, so you know which part is which.
Right.
So again, we'll just send that into the network because we've put the signature in there to unlock it. We'll send that into the network, and eventually the transaction will get mined, and it will extend the graph like so. Yep.
So every node in the network actually is responsible for checking the validity of this transaction?
Yes, every node will check. Yes, that's correct. Yeah, it'll check it'll validate every single transaction it receives.
Okay, so if I meddle with the script sig, it will flag it, and the node itself will ignore that transaction.
Yes. So if you tried to, if you sent a
wrong
if it didn't, correct.
Got it.
Yeah.
And that script sig is basically it's a digital signature, which is nothing but you're the hash of the transaction that's signed by the private key.
Yes, basically, yes. that's correct.
Okay. So the intuition is that what the node might be doing is it will probably re-sign it using the public key and check if both are equal.
Yes.
Or something like that.
Yeah. So that's correct. You figured it out. Yeah.
Something like that. Yeah. And coming back to this slide, so the previous one. So when you are actually, so you were talking about the placeholder, something about a placeholder. Could you just repeat that? I mean, is there some placeholder text that's put, or is it just empty?
No, the placeholder is the so if we go back quite far back, when we created this lock here, we put some locking code.
Correct.
So for example, let's say you want to spend this input. So let's say we are spending this input here. The placeholder is the code inside this lock, like so.
Code inside that lock. Okay.
Yeah, it's a bit confusing. I don't know. I'm not sure why it. I don't know why it has to be the code inside the lock. I'm sure it could be anything else. But there just needs to be, if anything, it's a bit awkward, to be honest. It does make creating transactions a little bit more awkward, having to go back and get the actual locking code for this input and use that as a placeholder.
Got it.
But that's just the way it works.
Sure. And we hash this, basically the whole thing in black, and that's what we sign. That's what we sign. Yeah.
So I simplified it by saying that you just put the transaction data into the elliptic curve, which is kind of true, but to be more technical and correct, you actually append a sig hash type, then you hash it, and then that's what goes into this elliptic curve mathematics. Got it. And you can go on. And you can usually find a library for it's called ECDSA, elliptic curve digital signature algorithm, and it's usually a library you can use to do this signing.
Sure. And one more question was that we keep doing this for every output that we are trying to spend, right?
So for every
we repeat this.
Exactly. So for every input, what you do is you will where's that slide gone? Yeah, you basically don't forget to remove all the existing signatures. So you'll sign each one, and then for each one you want to get the blank structure and then sign that for each individual one.
Got it. So we'll then at the end plug in all the signatures one after the other.
Yes, you just shove them into their space. So in this one I only had one. So let's say we had multiple. This is one done. What I'd do then, if I had another input, I would just take all this signature out and I would just sign the next one, put the placeholder into the next one, sign it, get the signature, and so on and so on.
Got it.
And at the very end, you'll just plug in the
and at the end, you just shove in all the script sigs in the transaction.
Shove them back in. Yeah.
Oh, got it.
Okay, so just to summarize, this was our transaction. We created that signature. We'll put it in there. So like I said before, transaction has four major parts. You have the version, you have the inputs, and the input has their own sort of mini structure, their own substructure. So it has it refers to a transaction ID, then it refers to a specific output, then you have a variable integer to tell you the size of the upcoming script sig, and then after that you have a sequence, and that's an input. Next up we have outputs, and they have their own structure again, but they're quite simple. They just have a value which is 8 bytes long. Then you have a variable integer to tell you the size of the upcoming unlocking code, which is called the script pub key. And then finally you have the lock time, and that is a transaction, and they're all the same. The only difference is they have varying number of inputs, varying number of outputs, and they obviously refer to different transactions and have different signatures. But if you understand the structure, then you understand the structure of every single Bitcoin transaction that there could possibly be, except for SegWit. This is like an old style transaction. You do have segregated witness now, which basically on a very basic level all it does, instead of having this signature code in the middle of transactions, it basically gets moved to the end of a transaction, and that's called the witness. So that's why it's called. It's basically like separating the signatures from the transaction, or sometimes a signature is called a witness, and that's why it's called segregated witness, because it's segregating the witness data, the signatures, from the structure of the transaction. I think covering segregated witness would be his own video, but I want to do this. Or this is a basic transaction, and these are still valid, and you can still make these transactions perfectly fine on the network. Yeah.
So maybe just in one line, it's basically a Bitcoin proposal.
Yes. Segregated witness is a change to the transaction data structure, and it just it just moves the. So you have this is like the typical basic transaction, but a segregated witness will have another field or section called the witness area, and the signatures basically get moved to the end of the transaction, and that's called the witness area.
Right. So, let me rephrase the question. This is a change in the Bitcoin core code base, or is it a change that exchanges need to make?
It's
because I keep hearing this, that this person has to implement SegWit, that person has to implement SegWit, and they haven't done it, and I'm still a little confused. But anyway, we can. Yeah. Well, if you don't have the answer, it's fine.
If you created your own software, and you've only ever been able to create these kind of structures, transactions, then you would have to, unless you're using the Bitcoin core software to create your transactions, which, if you've made your own software to create these, then you'll need to write your own software to create your own segregated witness transactions.
Got it. Yeah, makes sense.
In fairness, technically, I don't think they're terribly difficult. So I don't know why some places are taking so long. I think it might be just caution, maybe. I'm not sure.
Got it. Got it. So at this point of time, if I send a transaction with segregated witness, the Bitcoin core will understand it.
Yes. Yep.
Okay. Got it. Makes sense.
Right. So that's that's what we've done. So that's the basics done, and that's the data done. So what I'm going to do now, I'm going to do some examples just to create a transaction from scratch. Right. So this is my website. Before I do the transaction from scratch, what I would say is, here's a page. If you go to the glossary, go to transaction data, I've broken down the transactions here. So if you wanted to decode your own transaction, which I think is a good idea, I think decoding this transaction data is a very good place to start. I think trying to build one because of the signatures is a bit tricky. You might get a bit stuck at some point, but decoding it, I think, would be a good place to start for getting to grips with how transactions work. And it's always handy to have your own decoder just for your own reference purposes. But if you wanted to, dig into the transaction data, here's the page on my website. Or alternatively, you could just look at any block of transactions on the browser. So for example, this one, this is a bit of a complex one. It's taking loads of inputs in and spitting loads of outputs out. But if you click on serialized, you can break down the transaction into its component parts. So that might be helpful when you want to understand the structure of a transaction. But what I'm going to do now, I'm going to construct my own transaction. I can't get rid of this little thing here. Sorry, don't know how to do that. Brother. So I've got some. I've made a little script called Transaction Builder, and I'm going to build my own transaction. So first thing I need to be able to know which outputs I can spend. So luckily for me, I've created a transaction beforehand, and I've locked these outputs to addresses that I own. So I'm going to spend one of these outputs. So I'll spend this one. This is the one I want to spend and send to somewhere else. So first of all, in the transaction builder, first thing you need is a version number. So I'll stick the version 1 in there. And so that has turned that number 1 into hexadecimal network byte order, and it's turned it into a 4-byte field. Next up, we need to select the inputs. So I need a transaction ID and a output number. So this is the transaction ID. I'll put that in there. And I want this one here. So that's output 0. So there we are. That's the only one I want to spend. So that's that done. So if you look here, that's the number of inputs. This here is the transaction ID in reverse byte order. So A4, A4. And this here is the 4-byte this is the 4-byte output number. This here is the variable integer to tell me the upcoming size of the signature, but I haven't put it in there yet, so it's 0. And this is the sequence number that I'm not using. So next up now, I need to choose I need to create my outputs. So this one here, this is 0.05 BTC, but I want this to be in Satoshis. So let me just convert that. There you are. So that's 0.0051. So I'll put the value here. And the address I want to send it to, I think I'll send it to my donation address here at the bottom of the website. So there we go. But because I want this to get mined, I haven't put a fee on this. So what I'll do, instead of sending the whole amount, I'll send, say, 49 this amount. So that puts a little fee on it. I don't know what that's going to be in fee per byte, I'm just guessing, but that will leave a remainder in the transaction. And then again, put the address there. So that's the output created. Last up then, so this is the output, been added to the transaction code. One output. This is the... Is this right? Yeah, I'm sure it's here somewhere.
So a quick question here. So at this point, is it signed, or it still needs
it still needs to be signed. You have to create the whole structure first before it gets signed.
Got it. So has your code just plugged in the placeholder
Not
at
yet,
this
no.
point?
It'll do that in a moment.
Not yet. Okay.
So last up is the lock time. So there we are. So now we've created the structure. We've chosen the inputs and we've created the output from it. So now we've got the whole structure. We've got the data we need to be able to sign it. So to be able to sign it, I need the private key for this address. You should never expose your private key, but in this example, here it is.
Yes.
This is my private key for this output. So there we are. That's the private key that corresponds to this address. But like I said, we need to get the locking code so that we can use a placeholder when we sign it. It's a bit annoying, but if you click on this little lock here on the browser, this is the locking code. As you can see, those, it corresponds to opcodes, and this is the public key. That's the address. So I need this locking code to be used as a placeholder when I sign the transaction. So there we are. I'll sign this now, and this is the completed transaction data. So because this is all signed, this is ready to go. I can use, if I want to, I can just quickly decode it. So I've written my own transaction decoder. It's quite handy to have. So I can look at this, and it's showing me the inputs. There's one here, the transaction ID, and one output, and it's being locked to this address here, the BO address, which is my donation address. If you do Bitcoin CLI, if you download Bitcoin Core, it has its own decoder, decode for transaction, and you can do the same thing, and it will decode it for you as well.
Oh, nice.
So now we've got the transaction, it's all been signed and ready to go. What I can do, I can go Bitcoin CLI send raw transaction. So I'll put that in there, and there we are. it has just given me a transaction ID. So this is the transaction, and this is the transaction ID for it. So I can take this transaction ID, and I can go into my blockchain explorer, and I can enter the transaction ID, try and find it. Okay, it hasn't found it yet. It's probably taken some time for it to propagate the network. So I keep refreshing. Okay, give it 10 seconds. Go on.
So we are looking for this in the mempool or in the blockchain.
This will have
itself?
gone. So I've created this transaction. I sent it into a node, and this now going to be being sent on the network, and it's going to enter this node's mempool. So it should be appearing. If I click on this memory pool, it should be appearing.
Somewhere here.
So I just deleted the page.
Is there? Okay.
So there it is. There we are. It's just received it 5 seconds ago. There we are.
Oh,
so
nice.
I can click on this now, and there is the transaction I just made on the blockchain explorer. So now it's on the network. Now I know it's been sent on the network. It's a very low fee. I don't think it's going to get mined. But again, I can just look at the code, and this should be the exact same code that I created. So basically, you send code into the network, and that describes this transaction, the movement of inputs to new outputs. Go on.
Is there a converter to US dollars here? I mean,
I haven't. No, that's a good request. My brother asked me the same thing. I'm still working on it. But I think this is about $80 at the moment. So I'm probably going to want to make sure this transaction gets mined before I put the video out, because
exactly before you upload the video.
Because I've given away my private key.
And how? And what is the fee? Like approximate 0.0002.
Okay. Well, it works off fee per byte, because a node can only fit up their block with so many bytes. Actually, that's changed now. It's more fee per weight, but I haven't updated the Explorer to use weight, and it's more of a complex thing to use. But if you look at all these transactions, if you go towards the bottom, they're generally ordered by their fee per byte. There you are. The smallest ones are about 100 odd, 0.00100 satoshis.
Got it.
So, some will get included for less. But this is just a rough estimate. But it looks like my transaction is just slightly too low, the fee, to get mined just yet. So I could create another one, just to show you. But I mean, that's good enough, just to show you that how when you create a transaction, it just goes into the memory pool, like so.
Okay, in the memory pool, yes.
I've made this code available on the website. So if you go to code transactionbuilder.rb, the code is all here. I've written it in Ruby. I tried to make it as simple as possible. I did want to do it procedurally, because I thought that'd be an easier way to do, but I couldn't do it that way. I thought it seemed easier to do it in an object-oriented way. So it's not terribly long. It's about 300 lines long, the code. But the basic parts is I start with some utilities just for getting all the data in the correct format. Then the main transaction class that has version, inputs, outputs, and lock time. So it has an array of inputs, an array of outputs. So and then you have an input class which has the transaction ID, the vout script sequence, and then you have an output object which just has a value and the script pub key. And so if you want, I think it'd be good to create if you wanted to build your own transaction builder from scratch, I think it's a good way to do it, in your own programming language. But if you wanted to see if you're making some mistakes, you want to see where's going wrong, you could always come in here. For example, probably the trickiest part is just this signing part. Obviously, here's the signing method, and it's a bit long, but it's just basically getting all the data in the right order. I've heavily commented it, so it might be helpful for trying to figure out which parts you might be missing.
Right.
So, is there any questions with that?
No.
Oh, thank you. Yeah, awesome. I think that basically covers. If you wanted to create your own transaction, this should. It's quite I think my website's quite helpful for finding the correct data to be able to create your own transactions and just browse it and see what's going on.
Definitely. Are you using some sort of API, or is this being pulled from like a real node?
Yeah,
Like,
this is basically running off a Bitcoin Core node. But what I do,
okay,
I put it into my own database, but it's basically running live off a Bitcoin Core node. So when you make a transaction, so this is a new block
okay,
just been added. So yeah, it's all live.
okay. So you're hosting the website on the same node, or it's on a different machine, and you just pull data into a database and then have the website read data off the
It's
database.
actually on the same machine. It probably would make sense to have the node on a different machine, and then have the
Okay,
data, have
okay,
this website just reading the database. But I don't.
got it.
The machine seems to be handling it okay. So at the moment.
Wow. Okay,
But this
okay,
is running off a machine
cool.
in Switzerland, so that's why when I made this transaction, I'm in the UK at the moment. I sent it from my, I sent this from my local node from the UK. So, yeah. But then again, it only takes a
Right,
few seconds, I
right.
think, for a transaction to propagate the entire network. So it might have just been my website was a little bit slow at decoding the transaction and then storing it in the database.
Right, right. So, does the Bitcoin CLI give you access to all this data, like memory pool and transactions in the memory pool, or you had
Yeah,
to?
it does give you all the data. So I mean, you could use the website, but you can actually get all this data from Bitcoin CLI. I'm not sure what it is.
Right.
Oh yeah, okay, that's the mempool. So Bitcoin CLI get raw mempool. These are all the
Got it.
transaction IDs currently in there.
Got it.
Um,
Got it.
yeah,
Right.
and if you wanted to get Bitcoin CLI get raw transaction, there we are. So that's the transaction data for that one I just selected. So it's all there. You know, you can get all the
Right.
data out of
It's all
the,
there. Right.
the
Right.
Bitcoin CLI.
Nice.
Yep. So I think that's everything I wanted to cover. Anything else at all before?
No, that's it. Craig, thanks a lot for
No
this
problem.
again.
No, it's
And yeah, looking forward to others
yeah. I think
at
the
some
next one
point.
I'd like to
Yeah.
do is
Yeah.
probably covering the keys and addresses. So these public keys,
Definitely.
you got
Yeah.
public key, and address, how they all connect together through this, this elliptic curve, how they're created, because that'll
Right.
explain a lot about how this signature stuff works. Because at the moment I just sort of said this is a signature and it works, but I could explain how
Right.
it actually does work using this mathematics.
Nice.
So
Yeah, looking forward to it, man.
yeah.
Yeah, just let me know whenever. Yeah, whenever you're ready, and
I'll
we
start
can join.
working on it. I'll
Yeah.
start chipping away at some keys and addresses stuff. But if I give you an email in a while to let you know when I think it might be ready, yeah, we're good.
Sure.
Thank you very much. Yeah, thanks for
Cool.
listening. That was really good.